Hello, my name's Isaiah, and this is Brandon, and today we'll talk about applications of message passing. So our group was particularly interested in a topic called linear logic, and one of the most fascinating areas in linear logic is this mathematical construct called the linear category. And what makes linear categories a very nice mathematical construction is it gives us a nice and formal framework to describe horizontal, if you will, um, horizontal communication of information. So last week during research week, we set out to study the application of message passing to some protocols, but instead of using the full framework of linear categories, we used a framework developed by Chad Nestor called the free cornering, which is intimately related to linear categories, as the horizontal component of free cornering is linear category. So in this short presentation, we will cover three topics. We'll discuss what a free cornering is. We'll give a real-world application. And if we have time, we might discuss free cornering with choice when the base category that we're working with is compact closed. So to get started, we need to think, what exactly is the information we want to communicate? And what we are actually communicating are resources, and the structure we'll be using is called the resource theory, and that's really just a very fancy name to a very simple categorical structure. It's actually just a freely generated strict symmetric monoidal category where the objects are resources like egg, pepper, or stove. And the morphisms are processes that transform resources. So for example, we might have a morphism like crack which denotes the process where we crack an egg and turn it to yolk. Or you may have a process like fry, where we take the yolk and a stove and get sunny side up in a stove. And we interpret tensor to be and. So we would say egg tensor pepper represents having both egg and pepper. So before we can actually define what a free cornering is, we'll need two mathematical constructs. We'll need a double category, in particular a single object double category, which will consist of three key pieces of information: two monoids, which we call a horizontal edge monoid and a vertical edge monoid, which are, if you can see, here and here. And a collection of cells. So if you know monoidal graphical calculus, you can think of reading these cells top to bottom, and this is sort of your regular diagram, except we have these two side lines, and that will represent our communication of information from one cell to another. So the objects on the top and bottom cell come from a horizontal monoid, and the objects on the side cells come from our vertical monoid. And of course, we can compose these cells horizontally and vertically. The second structure we'll need is a pro-arrow equipment. So a single object double category is a pro-arrow equipment when for every object in our horizontal monoid, we have this A white circle and A black circle in our vertical monoid, and we have these four cells. So the interpretation for this free cornering, as we'll soon see, is that A white circle will represent sending a resource from left to right, and A black circle will represent sending a resource from right to left. So for example, this corner cell here, if you can see my mouse, yeah, will represent taking a resource A and sending it from left to right. And these corners need to satisfy a handful of what we call yanking equations, and they actually have a very natural interpretation. So for example, this one on the far left is just saying that if we receive info A from the right, and then we send A from left to right, then it's like doing nothing, which is sort of what we would expect. So with that intuition, we're now actually going to describe this monoid, which will encode the data we need of sending information. In particular, we'll have this A-valued exchanges, which is just a free monoid created from the set where we have, we're created by taking every object A and having an A white circle and A black circle. So the intuition is that elements of the A-valued exchanges describe a sequence of resources moving between participants in an exchange. So here's just an illustration of one object in this monoid A-valued exchanges. We have A black circle, B white circle, and C white circle tensored together. And what that really denotes is if we have Alice on the left and Bob on the right, it denotes Bob sending A to Alice because it's a black circle. And because the other two are white circles, those represent Alice sending B to Bob and then C to Bob. So that's what an A-valued exchange is. So now we have the necessary structures to create a free cornering. And so to do that, we start with a resource theory, which as you remember is just a strict symmetric monoidal category. And we define pro-air equipment A, where we have a horizontal monoid, which just inherits the monoidal structure from the base category A. We have a vertical monoid, which are just the A-valued exchanges. And then we have these generating morphisms, which are the white corners and the black corners, along with the vertical cells for each morphism in the base category. So if we have a morphism F A to B, we have this vertical cell, and they need to satisfy a bunch of rules to behave nicely. For example, the vertical composition of vertical cells needs to be the vertical cell of just the composition of the morphisms in the base category, and we have similar results for identity and tensor, similar equations. So how does a free cornering capture concurrency or message passing? The interpretation you should have is that the horizontal monoid of the free cornering represents the resources, and the vertical monoid of the free cornering represents the channels where we're sending information. And the cells are what Chad Nestor called concurrent transformations. And what these cells do is they describe a way to transform the top elements, the top resources to the bottom resources via information being passed from the sides. So here's an example where we crack an egg and we then send the yolk to the area of the stove where we fry it. But there's one ingredient missing in this framework, which is the ability to dynamically choose which resource we want to send. Unfortunately for our group, Chad Nestor solved that a few months ago with a paper describing free cornering with choice, and he also did with iteration, but for now we're just going to focus on choice. So basically, when we have we start with a symmetric distributive category, and in this case we need a distributive category because we'll have a notion of or, so we can have egg or pepper, which we denote with O plus instead of O times. And we have just a regular free cornering, and we add to our regular free cornering a few additional properties. First of all, for all pairs of A-valued exchanges UV, we add these U plus V and U times V objects, and these will be the types we'll use for a choice. And then we have three properties that give us our choice. So we start with first choice on the left, which is mathematically given by this diagram. So basically for all cells alpha and beta that only differ by the left boundary, so you have X here and Z here, there exists these injection-like cells, which are represented by these upside down pies. and a unique cell, alpha plus beta, such that when we apply these injection-like cells to this unique cell, this unique composite cell, we actually recover alpha and beta. So we basically have this choice, this ability to choose which morphism we want. And then we just have a few more of these properties, but they're just for the different sides. This represents on the right. So we have two cells just different by the right. And instead of having upside down pies, we have pies that act more like projection maps and go on the other side. And similarly, we have choice on the top, where we use these injection maps on the top, denoted by sigma, to recover alpha or beta. So that is the general framework we used in our research. So now we're going to actually see what we did to apply this framework to a real world problem, and I'll hand over the microphone to Brandon to explain that.
Thanks, Isaiah. So, yesterday you saw I'm an engineer, so I'm trying to study processes in complex systems, and we've been using, the symmetric monodal category formalism to try and represent processes. But what that doesn't allow me to do, as Isaiah was pointing out, is sort of decompose the different subsystems and figure out how they're all working concurrently as one process. And so that's where we really wanted to apply this framework to an actual problem that I've been working on as an engineer. And so this has real sort of meaning and implications for safety and health of people working in, manufacturing facilities or plants where there's operations that are hazardous and we need to have safe protocols. So the situation, we call it isolation of hazardous energy in industry. And what this means is occasionally a human has to go into a tank or a confined space, as we call it, to clean a tank or perform a service on equipment. And sometimes that equipment has other sort of things going on, like rotating devices that are, connected to power sources. And so we have a very manual protocol today where humans have to sort of make sure and guarantee that the system is safe in terms of power is off when a human enters, right? Because we don't want them to get sort of caught up in the rotating equipment, for instance. And so I've seen this happen before, like the accidents can happen. And so what we're looking for is a more formal way to describe this exchange of information in these sort of concurrent choices that are being made. And can we represent in a way that can sort of guarantee that only when the system has reached a safe state does the human enter to perform the work. And so I've been sort of using other formal methods like model checkers and sort of Petri nets to try and find the right abstraction for this. And we thought it was a good chance to try out a ACT framework. So this is sort of the conceptual sketch of what's going on here in this example. Imagine you've got two pieces of equipment, a tank and a power source that's sort of feeding power into the tank. Now imagine that the tank is sort of able to check and inform a worker who's over that piece of equipment whether or not it's clean or needs service, right? So we see that sort of information being passed, that signifying to Alice that the tank needs cleaned. And so what Alice needs to do is sort of generate we call it a work order, like somehow communicate with Bob to say, because Bob's controlling another piece of the facility, which is the power source, and say, hey, can we turn the power off, shut it down, so that I can then safely enter the tank. And so we want a formal way to describe this process and its sort of concurrency so that we don't run into a situation where someone enters the tank when it's in the system is in an unsafe state. And so, we'll put this framework to use. So we define our category, isolation of hazardous energy, as the free, strict, symmetric monodal category. And as objects in this category, we're considering the states that I was sort of describing. So whether the tank is empty or not, whether the power is on or off, whether the tank is dirty or not. So those are our objects in this category. And for morphisms, we're looking at processes that transform those states. So for instance, if I had the power was on and we shut it down, it's now off. And so we sort of can lay out those different morphisms. And this is sort of our finished product for the research week in a way. It's describing that full process, but now we have the ability to sort of show the subsystems that are each doing their individual thing, like the tank, Alice and Bob, right? So now we can able to represent those and then show, not only reading it top to bottom how the work is being done and as states are changing, but also left to right with the cornering concept that Isaiah was describing to show how information is being passed along. And so, just sort of to walk through this very quickly because we're sort of short on time. If you start with a tank, you can sort of check to see if it's clean or not. From there, if it is in the state of it needs service, then it creates a work order, which is then copied. Copy is sent to both Alice and Bob. That lets Bob know to shut down the power. And once all those conditions are met and the safe enter cell, then Alice can enter the tank, perform the work, and then everything sort of updates and propagates through. And so that's sort of our industry example, and I'll turn it back to Isaiah to take it home.
Yeah, so basically how the circuit is working is it's just a very complicated conditional. So each of these cells can be broken up into simpler cells. So if you look at safe enter, this is representing when it's safe for Alice to enter the tank. And there, you can see that there are a few conditionals. So remember, plus was the type representing a conditional. So here we have, for example, around safe enter, we have a choice between having a work order and we're using monoidal unit for not having a work order. And on the right, we have the choice of the system being on or off. And then we sort of propagate those choices down. So in the next slide, I'm going to show exactly how we guarantee that we enter safely. So here's how the safe enter is defined. Remember the uniqueness property from the free cornering? Well, what we're going to do is we're actually going to define the safe enter cell for every single possible choice. So in this case, what we're going to define safe enter when we choose work orders or when we have a work order, when the tank is empty, and when the power is off, we know it's safe to enter and we should enter. Otherwise, we basically do nothing. We just propagate the choices down. Now, one of the things to note about the way we're formulating things is we start with these input choices, and when we evaluate, the choices sort of propagate through the cells. And actually, that is how we think we can create a formal way to verify whether a system is safe. So for example, we can say that if we start with one of these check mark states as an input, well, and all of those represent safe starting states. Remember that sigma 1 and pi naught here represent the power being on and the tank being occupied, which is something we don't want. That's why there's X's next to them. So if we start with one of the checkmark states, you can show that this cell will remain in a checkmark state. And if you compose it with another cell that is safe in this sense, then you're going to get another safe cell. You're going to get a safe composite. So you have this composable safety, which we think is interesting. So how much more time we have?
I think this is probably good.
Okay, so I think I'll just briefly mention the next topic. So that was how we were applying this free cornering to these real world problems, but we also wanted to apply it to a little less real world problems. So what we want to do, another thing we want to model is quantum protocols and use this free cornering framework to express those. And the natural choice would be to have as the base category the category of finite dimensional Hilbert space, or FD-Hilb. Now we haven't worked out the details, assuming the base category is FD-Hilb, but we started with just showing what happens when the base category is compact closed. So I'll just briefly mention, I won't go over all the proofs, but one of the things that Chad Nestor showed, I think back in 2022, is that if the base category is compact closed, then if you just take the horizontal component of the free cornering, and what that means is just the collection of cells that are purely horizontal, then you get a symmetric monoidal category, and you get a category that is compact closed, more importantly. But what we wanted to do is we wanted to expand the result a little bit. We wanted to show that similar, we have a similar theorem if we are using the free cornering with choice added. So we have some math, which I'll skip. And we basically have this interesting result that if the base category is compact closed, then the horizontal component of the free cornering with choice added is also compact closed. And as the final result, which I think is personally one of the coolest results we found, since the category is compact closed, we can talk about transposes. And you get this interesting relationship between choice on the left and choice on the right. In particular, what you get is that this upside down pi naught function, if you consider the upside down pi naught function, which is our choice on the left, and we take the transpose of it, we actually get the pi map correct in the correct orientation. And so you have that interesting relationship. So that's our talk. Those are the results we found. And here are the references we used.
Thank you, Brandon and Isaiah. So we have room for one quick question. All right.
Hey, yeah, this is great. I've got to put on my engineering hat for a second. And so I kind of have a question. It's kind of a two-part. One is, can you start reading that diagram from the middle?
Yeah, let me just, sorry, I accidentally closed the Zoom.
Question. All right.
Hey, yeah, this is great. I've got to put on my engineering hat for a second. And so I kind of have a question. It's kind of a two-part. One is, can you start reading that diagram from the middle?
Yeah, let me just, sorry, I accidentally closed the Zoom. Okay, so the big diagram, the messy one?
From the
This
right.
one?
And the reason why I say that is because I'm thinking about fault tolerance, and I'm thinking about the case where maybe there's some sort of power jitter, and now maybe some of the states that you've been propagating through, and you're in the middle of some chain of computations where you're trying to figure out if it's safe to enter. So, yeah, I'm thinking about fault tolerance of this system in practice.
No, I think there's a lot of work to be done to sort of apply it in an actual application. We just wanted to see if even this framework could even represent this sort of protocol. Like you could represent this in a number of different ways, as you would like software model checkers or something. But yeah, I mean, that's definitely something to consider.
Great. All right. Thank you. Thank you. And this group was mentored by Priya. Do we have anyone from Barbara's group in person, or are they all on Zoom? Okay.